I hope you're all doing well. On this channel, I share videos that highlight the importance of mathematical modeling techniques. Starting with this video, I will begin discussing the content of two papers I have published on Zenodo regarding the Collatz conjecture. To make the explanations easier to understand, I will walk you through concrete examples along the way. I hope you will stay with me until the end. The Collatz conjecture is an unsolved problem concerning how numbers change in an iterative calculation that begins with a positive integer, namely, a natural number such as 1, 2, 3, and so on. When a number that appears as odd, you multiply it by 3 and add 1. In this case, the value becomes larger. On the other hand, when a number is even, you divide it by 2, which makes the value smaller. The Collatz conjecture asks whether, no matter which natural number you choose as the initial value, the sequence generated by repeating these steps will eventually reach 1. I uploaded my first paper on March 15th of this year. The title of the paper is as follows. By carefully observing how the numbers change during the iterative process, I noticed that the calculated values behave as if a monkey were walking across a tightrope, shifting up and down, yet eventually making their way to 1. I named the set of natural numbers that form each rope a Collatz rope, and I expressed the numbers that appeared during this tightrope like progression in mathematical form. From this expression, I derived an inequality that determines whether the calculated value can reach 1. I then examined this inequality and demonstrated that it is satisfied for all natural numbers, thereby proving that the Collatz conjecture is true. On May 22nd, I released another paper with the following title. In this paper, I summarized the content of the previous report and presented clear evidence supporting the validity of the Collatz conjecture. From here on, I will explain the contents of the two papers in order as a series. The first paper is quite extensive, consisting of 47 pages of main text and 37 pages of supplementary material, so it will likely take a considerable amount of time to cover everything. The second paper is only 11 pages long. However, in order to understand its content, it is necessary to grasp the meaning of the mathematical expressions presented in the first report. I will now begin explaining the content, starting from the first paper. Its structure is as follows. In the first chapter, I concisely introduce several past studies, state the fact that the Collatz conjecture remains unsolved, and clearly present the structure and objectives of the present paper. In Chapter 2, Theory, Section 2.1 begins with an explanation of the calculational algorithm of the Collatz conjecture. In Section 2.2, I present the calculational examples referenced throughout the discussion and describe the existence of natural numbers that temporarily increase during the iterative process, which is defined as temporarily rapidly increasing numbers. Next, in Section 2.3, natural numbers are divided into odd and even numbers. The odd numbers are further separated into two groups, A and B, based on the different behaviors they exhibit during the iterative calculation, while the even numbers are represented by C. Group A is subdivided into more detailed categories. In Section 2.4, I refer to the flow of calculations using these values as operations, and I define the Collatz operations A, B, and C. Operation A is further classified into finer subtypes, and each operation is categorized according to differences in calculational behavior. Finally, in Section 2.5, when the calculated value is denoted by x, I define th equation applied when x is odd, namely, y equals 3x plus 1 as the tightrope walking equation. To strengthen both the validity and generality of the proof, I decided to examine not only this basic equation, but also other TW equations. For this purpose, I expressed the general form of a TW equation as y equals 5x plus 1, and I state in advance that In addition to phi equals 3, I will also discuss the cases phi equals 1, 5, and 7. In Chapter 3, I present the examination and discussion. In Section 3.1, I show that in the iterative calculation performed with any natural number as the initial value, all numbers that appear on the way from the initial value to 1 are composed of combinations of the four Collatz operation types described above. In Section 3.2, I explain that when the initial value changes, the Collatz operation types assigned to the calculated values may coincide at first but eventually diverge. Because of this divergence, it becomes difficult to express the progression of calculated values using a single equation. Consequently, it is also challenging to prove that the calculated values converge to 1 using only the standard mathematical approach of evaluating limits. In Section 3.3, I discuss the convergence of calculated values using 4 types of Collatz operations and 2 different dynamic models. In Section 3.3.1, I determine the rate of change in the value produced by a single application of each Collatz operation. In Section 3.3.2, I show that when these rates of change are applied to iterative calculations, the final value becomes exactly 1 in the case of strict computation, and that values close to 1 are obtained even when approximate rates of change are used for calculational simplicity. I thereby establish the validity of the derived rates of change. In Section 3.3.3, I show that when the Collatz operations appearing in a sequence of iterative calculations are grouped by type, the proportion of each type closely matches the natural proportion of odd and even numbers. I note that this result is expected since the types of natural numbers selected by the Collatz operations naturally follow the underlying ratio of odd to even numbers. In Section 3.3.4, I construct 2 types of dynamic models and perform simulations of the iterative calculations using the average rate of change per Collatz operation. These averages are derived from the observed frequencies of the Collatz operation types for phi equals 1, 3, and 5. The simulations reveal that the calculated values decrease for phi equals 1 and phi equals 3, while for phi equals 5 they increase without bound. Since it has been shown that the changes in the iterative calculations starting from any natural number are composed of the 4 types of Collatz operations, the results obtained from the dynamic model simulations, namely, whether the calculated values ultimately increase or decrease for each value of phi, can be regarded as fundamentally valid. However, because the simulations use average rates of change, they do not constitute a mathematically rigorous proof. In Section 3.4, I carefully examine how the calculated values change and point out that they follow a consistent pattern. I then define a set of numbers that I call a Collatz rope. A Collatz rope consists of an odd number at its lower end and an infinite sequence of even numbers extending upward from it, each obtained by multiplying the odd number by a power of 2. In other words, it represents the set of natural numbers that lie along an infinitely long rope extending upward from a terminal odd number. During the iterative calculation, the calculated values move along these ropes as if walking a tightrope, and eventually they grasp the rope whose terminal value is 1 and descend along it until they reach 1. In Section 3.5, I present an example showing how the calculated values actually travel along a Collatz rope and eventually reach 1. I also describe the software I developed to perform the Collatz calculations on a personal computer. From sections 3.6 to 3.10, I describe 5 representative characteristics of the Collatz ropes. In section 3.6, as characteristic 1, I show that the iterative values travel along a Collatz rope and ultimately reach 1. In section 3.7, as characteristic 2, I prove that the same Collatz rope is never used again once it has been traversed. In section 3.8, as characteristic 3, I discuss the ratio are of even to odd numbers that appear during the iterative calculation. In section 3.8.1, I define R and examine how it can be calculated. In section 3.8.2, I show that when an initial value is taken sufficiently large for certain classes of natural numbers, R converges to a value near 1.5 when phi equals 1, and to a value near 2 when phi equals 3. In section 3.8.3, I examine the appearance ratios of odd numbers A and B and even numbers C in the iterative calculation, as well as the appearance ratios of the Collatz operations A, B, and C. I show that these ratios approach constant values as the number of iterations increases, and I also derive the relationship between the two sets of ratios. In section 3.8.4, I estimate the appearance ratios of the Collatz operations A, B, and C for sufficiently large initial values, and I show that the resulting theoretical value of R becomes 2.1. I also derive theoretical appearance ratios for odd numbers A and B and even numbers C, and I note that these theoretical values agree with the calculated results. The value of R obtained here corresponds to the case in which the initial value approaches infinity. In section 3.8.5, I describe another method for computing R using the dynamic models introduced in section 3.3. This approach also yields a value close to 2.1 for phi equals 3. This result suggests that, despite being an approximate model, the dynamic model captures behavior that closely resembles the actual changes observed in the iterative calculations. In section 3.8.6, I examine the values of R for phi equals 1 and phi equals 5 when the initial value is taken sufficiently large for certain classes of natural numbers. I show that our approach is 1. 477 for phi equals 1 and 1.956 for phi equals 5. That is, these values lie near 1.5 and 2.0, respectively. In section 3.9, as characteristic 4, I discuss whether the iterative values always reach 1. In section 3.9.1, I derive a criterion for determining whether the calculated values eventually reach 1. For phi equals 1, the criterion requires R greater than 0. Since the value of R, when the initial value approaches infinity, that is, the value of R infinity is 1.47, this criterion is satisfied, suggesting that the calculated values may reach 1. For phi equals 5, the criterion becomes R greater than 2.322. Because R infinity is 1.956, the criterion is not satisfied, indicating that the iterative calculation diverges. For phi equals 3, which corresponds to the standard Collatz conjecture, the criterion is R greater than 1.585. Since R infinity is 2.1, this criterion is satisfied, suggesting that the calculated values may reach 1. In section 3.9.2, the criterion for R is examined, and a general formula for the lower bound RL contained in the expression is provided. In section 3.9.3, the physical meaning of RL is investigated, and it is clarified that this value corresponds to the value obtained by applying only the TW equations to the initial value n, 1 times to reach its increased value, i.e., the maximum value, then repeatedly dividing it by 2 until it returns to the level of n0, and finally dividing this result by the number of applications of the TW equation. It is also shown that for phi equals 3, the value of RL is 1.585 when the initial value tends to infinity. In section 3.9.4, for phi equals 3, the range of possible values taken by RL, depending on the initial value, is determined. It is further stated that the relation RL holds when all natural numbers are taken as initial values. This relation constitutes a necessary condition for the calculated value to reach 1. In section 3.10, as characteristic 5, I explain that the iterative values reach 1 by following a unique path that depends on the initial value. In section 3.11, I discuss the merging points, referred to as grasping points, on the Collatz ropes that the iterative values hold onto while traversing the ropes. In section 3.12, I describe the values that are associated with numbers that exhibit temporary rapid growth. In section 3.13, I prove that the so-called BB pattern, where an odd number of type B is followed immediately by another type B odd number after applying Collatz operation B, cannot repeat indefinitely. In other words, the iterative calculation does not diverge through an infinite repetition of BB transitions. In section 3.14, I describe several characteristics observed specifically in the iterative values when phi equals 3. Finally, in Chapter 4, the conclusions obtained in this study are enumerated, and it is concluded that the Collatz conjecture is valid. The above constitutes the content of the main text, but additional detailed explanations are provided in the supplementary materials to aid understanding. I am not a mathematician. I am a chemical engineer who has conducted research using both chemical reaction experiments and mathematical modeling. Based on my experience, when I observed the changes in the calculated values generated according to the rules of the Collatz conjecture, I felt that they resembled experimental data. However, the behavior of the calculated values varies with each initial value and is too complex to predict. Therefore, I concluded that an environment was needed in which these changes could be thoroughly observed, and I developed a program in the C language. This program helped me construct mathematical expressions based on data observation and gain confidence in the correctness of the formulas I derived. The program is available on GitHub. Using this program, it is possible to perform calculations up to approximately 100 digits on a personal computer. By developing this program, I was able to examine not only the tightrope walking equation y equals 3x plus 1, but also other forms such as x plus 1 and 5x plus 1. In conclusion, the calculated values always reach 1 for both 3x plus 1 and x plus 1, whereas for 5x plus 1, they reach 1 only in limited cases and diverge in most others. By comparing these results, which obtained from equations that might appear irrelevant at first glance, I gained strong confidence in the validity of the Collatz conjecture. Starting next time, I will explain each chapter of the paper in order. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.